Welcome to the third project lecture. I've actually gone through all the hand calculations you're going to have to do your project. So this is for those of you who are interested in going out to practice and seeing how the computer software actually plays into this, as opposed to the hand calculations that you've been doing that I'm sure you're aware you will not be doing ever again, probably. The hand calculations you're going to do in these homework assignments for this project will probably be, I'm sure they're the first, and they will probably be the last time you ever do that. So that's why I like it when you really focus on it and make it look presentable and good, because it's for you, not for me. You're going to come back someday and need to see these calculations and actually understand what you were doing. Maybe for the SE exam, maybe for the first time you're going to do a post-tension concrete project yourself, and you're going to want to get refreshed. But I can't tell you, from a guy who's, as I sit here, 59 years old and done a lot of calculations, it does not take long to forget what you were doing in your calculations. If you go back even just 3 months and try to ask yourself, what was I doing? If you're not clear enough to your future self as you're doing these calculations, you can pretty easily get confused or lost or decide you have to start over because you really aren't sure what was going on. So anyway, here's PT data. My dad wrote all the code for this back in the 80s and 90s and did a great job. Along came we used it. The two programs that designed almost all the early post-tensioning, early being all the way up, I don't know, through 2005, 2008, was PT Data and ADAPT. And they did pretty much the same thing with some minor differences. It was before all the three-dimensional software and finite element stuff came out. I'm not really sure when that came out. I could be off on the years, but give me a break on that. Thank you. But PT Data and ADAPT were, frenemies. Bijan Alami and Florian Barth had ADAPT, and they were good friends with my father. They were all good friends. They were all participating in the explosion of the popularity of post-tension concrete. So there really wasn't competition necessary because there was plenty of work to go around. And at least in my dad's case, I know in Florian's case, the writing of the software was not the way they made their money. They made their money by actually being practicing engineers, designing all of this. The software was really written, I know in my dad's case, really just for himself. And then he sold it to friends who wanted it. But it was never the major source of his income, and it hasn't been a major source of mine either. I keep it updated and have done all the work that I have done on it, really just so that we here at Seneca can have a good program that we really like, trust, can do by hand, and are really intimate with. And we use it on a daily basis here, and that's kind of the user friendliness of it, is we can churn out a tremendous amount of work using this, what's now considered a relatively simple program. What I'm going to do here is just model and show you how I came up with the design example in the book. So new beam girder. I have two spans. If you recall, I said the default is going to be skipping the live load or patterning the live load. In this particular case, we just used uniform live load. Not really code compliant, but for educational purposes, just fine. 5,000 PSI concrete, limited both of the top and bottom stresses to 7.5 square root F prime C. In reality, we set this to 9 on the bottom in our designs, but we're in the academic world now, so we're just keeping the uncracked concrete top and bottom. In this example, we had used number 8s, top and bottom, number 3 stirrups. So this is all the setup that we had used. in the hand calculations. I opened it up in the screen to my left, so that's where this window is popping up. So 11 foot 4 is the column bottom dimension. It's also the column top dimension. The C2 column, the C1 is 24 by 24. Fixity means fixed at the far end. You're always fixed locally. There's no way to pin the member where it's framing into the column. You don't do that in monolithic cast in place concrete. But the far end, you have the option of having fixed or pinned. So that's what that is asking you. So our top column was the same, a 24 by 24, 11 foot 4 inches tall with a fixed far end. Our first span was 62 feet. Our second span was 44 feet. We're going to have to call this section something. We'll call it A. That's always an easy one. We have a variety of beam cross-section types to choose from. We are going to choose one. That's the one we used. We had 18-foot beam spacing, had a 36-inch deep beam, a 5-inch slab, a 15-inch web. And if we hit return, it will tell us what 16T plus the web width is. So we're all good. Keep going. Superimpose load for each span. By the way, PT data, you want to use the uniform load as long as you have uniform loads. You have other ways to put loads on, but this is the way. Using this button, it'll apply the load to all the spans. Regardless of how many spans you have and what lengths they are, it will correctly place them on the length that you have. So we had 2 pounds per square foot of additional dead load, and our live load was 40 pounds a square foot. And if you check the next span, 44 feet, it's applied that same loading to that span. Tendon profile that we used, because we're in the academic world, we're going to use 1. These are all the options we actually have. It will correctly do all the equivalent loads that you see if you choose that type. Academic world, this is a lot easier. 8FA over L squared. Okay, so that's all the input it took for this beam. We'll let it run. This is truly a design program. So it is doing the design for you. It intends to do the design for you. I think my father wrote this kind of being afraid of what would happen if people just had to wing it themselves. So this is early AI. So it's deciding what it thinks your first pass at this design should be. Now, it will come up with different strands in the 2 different bays. We had decided we were using 10, so we'll put in 10. This is fully draped. All of these numbers are from the top. There's a reference point in PT data that you usually place at the top of the beam. Some beams can step, some can do something different, so that's why you have to start with a reference point, and everything's measured from that. In this case, if I'd have left this as fully draped, we're pretty significantly overbalanced. And what we do here is keep a real solid eye, real close eye on the concrete balance load. That's actually about the most important thing we're really looking at as we're laying this system out, trying to figure out what we want to do. I've told you in the beginning, we're shooting for about 70% balance load. So that's how we came up with those 10 tendons, if you recall. And we're adjusting the drape to keep those relatively close to each other. It turns out that will give us a good design. Keep an eye over here. It will jump out at us and start shooting colors to us if we are stepping outside the flexural tension range. So just for fun, if I were to put that as 5 strands, it tells me right away that in the first span, at the mid span, I've exceeded the allowable tensile stress. So we don't want to do that. But so this screen is where the activity happens. It's where your participation happens. You're modifying, it's anchoring the system at the CGS at the end, so we don't have to do much with that. Actually, it rounds it. I think I want to put it exactly the CGS. Again, it's a design program for design firms, so it knows that you're not going to specify probably 11.4 inches. You're going to round to 1/4 of an inch. So, but we're being accurate here in the academic world. So these numbers might look familiar. This was the left side tensile stress that we calculated by hand of 0.088. We had a midspan maximum flexural stress of 268 psi and 173 at the right joint. So these numbers should look somewhat familiar to you. So really, believe it or not, we're done with the design. The design is finished. We can preview the graphic. And PT Data has done everything. It's done the stress checks. It kind of told us that the flexural tensile stresses were okay, which is all any normal design really cares about for satisfying the code. It's now designed, checked the minimum steel provided, checked against the demand moment, added it as necessary. Turns out it wasn't necessary in either any of the negative moment regions and in the positive moment regions, and it's already done the complete shear design, the VCN, VCI, VCW design, and calculated stirrups. So that's about the length of time it takes to do this. We can knock out 20 beam designs in the morning before we go to lunch. And that's really just the beauty and the simplicity of this. Now, for those of you working along and checking your values, these are the windows you'll want to look at. This is telling you what the center of gravity of the steel location is. So as I've mentioned a number of times as we were going through the project, you can use PT Data to tell you where the CGS is. So that you would get right out of this column. The first point that it always prints on either side is the face of the column. The second point that it always prints is h/2 from the face of column. That's true on both sides of every single span. So it knows that you want those values, and it gives them to you. Told you when you're checking your section properties, here's the area. This is the section modulus to the top. This is the section modulus to the bottom. Again, you don't need me. Your CGC is printed here. You can check all of your hand values with this. The moments, this is the moment chart for the span 1. This is the dead load. These are the equivalent loads. These two columns are the live loads. Now, since we are not skipping the live load, your maximum negative and maximum positive moments are going to be the same. So both these columns are identical. This is the secondary moment column. So for all those hand calculations that you're doing, this is where you will check and verify those. That's span 1, that's span 2. So if you remember, we calculated that 410.6 at the face of the column on the very left side, span 1. If you maybe recall, we were at 505.2 or very close to that with our hand calculations. Beam shears are the same thing. The first point is going to be the face of the column. The second point is going to be h/2. But these were the unfactored dead load, live load shears. All the flexural concrete stresses are listed here. So at the two ends, if you recall, our service stresses tension at the top, 088 and 173. I think we calculated 172, if I recall. But you have your maximum positive moment stress too, and that's what you're checking against your maximum span flexural tensile stress. That was 268. I think we got very close to that by hand. Next span, most of this is in direct compression, by the way. So that's where stresses are checked. When you're starting the project, the tendon equivalent loads, you can check those too. Now, I've given you the force and profile, but you are the one calculating what equivalent load that creates. So in the first span, that was 1.122, and you calculated it. You check it here. The concrete load, the program calculates for you. That's why we only put in the superimposed load of 2 pounds a square foot. Program calculates knows how much concrete there is and calculates that. And then this percent is just how much of this concrete load are we balancing with that tendon load. If you remember the next span, we were at 1.128 with equivalent loads. Span 2, same concrete weight. So in the factor load rebar review menu, this column is the demand moment. So when we calculated that demand moment, we were at the left side of the interior support, the span 1 side. So we actually calculated that 742.7 as the demand moment. This is where we would come to check that. The far right of this is the FPS value. So if you recall, at that same location, when we went to calculate the capacity of the section, we calculated an FPS value of 198.9, and this is where we would come to check that that was correct. So demand moment, and again, because we're not skipping any moments or skipping any loads, these are the same, and the FPS column. So the beam shear design, your VCN, VCW, and VCI values, try to recall if you can, but we did that at H/2 from first interior support on the controlling side. So we calculated a VCN value close to 97, I think it was 97.6. Calculated VCW 143.6 or something very close, and we were at 118 on VCI. We decided that that 118 controlled the design. We used that and came up with stirrups, number 3 stirrups, 2 legs of 24 inches on center. This is where all of that gets checked and verified. I will probably give you a project that does not result in minimum, or maximum stirrup spacing, actually. Minimum stirrups required. So you'll have a little bit more fun checking VCN, VCW, VCI, and some value here. So those are the review menus that you will be interested if you're working along. I always give out the printed values of this output, so you don't have to even use PT data. But for those of you who purchased it, if you're watching this through the SK Ghosh and Associates design program, you have this program likely, and you're working off of it to verify these things. But so that's it. That's PT data, and that was the slow motion version of how quickly I can design a beam. When we really get going, we can really crank these out, and there's no difference designing one-way slabs or two-way slabs. They go just as quickly. Same basic input altogether, same basic idea and principles. Okay, any questions? No. Okay, well, you're off and running on your project homework assignments. Good luck.